every device that we human beings have for measuring things has some limitations. For example, if I were using a ruler to measure the length of a paperclip, the smallest units on my ruler happen to be in millimeters. As I measure this paperclip, can I be absolutely incontrovertibly 100% confident that the paperclip is longer than 4 centimeters? Yes, I think I can. Past that point, however, my ability to be 100% confident starts to diminish. In this case, my paperclip appears to be about 4.5 centimeters. However, my certainty on the 0.5 is only an estimate. Why? Because of my eye's limitations, as well as the limitations of this ruler. It doesn't, for example, measure in increments any smaller than millimeters. For example, this paperclip might actually be 4.51 or 4.49 centimeters. So, given the limits of my measuring device here, I can't get any more accurate than just 4 with some degree of uncertainty built into the 0.5. In the world of science, it's understood, by scientists, that the last digit in any measurement, in this case 5, contains some degree of uncertainty. The number of digits that we report in a measurement of 4.5 is called that measurement's number of significant figures. The word significant in this context really means measurable. A measurement of 4.5 only has 2 digits, that is, 2 significant figures. Now, if you want to learn how to determine how many significant figures a given value has, feel free to click the link that I'm posting right here. Let's suppose, for example, that I had measured the width of a room to be 4.57 meters and its length to be 6.23 meters. If I were asked to report its area, what I would initially do, of course, is multiply the width by the length. If you do this on your calculator, the answer that you end up getting is 28.4711 square meters. But if I were asked to report this area in a scientific journal, would I write out the final area as being this? Assuming that whatever device I use to measure the width and the length of this room only has the ability to measure out 2 decimal places, that is as accurate as I can get in the length and the width of the measurements of the room. But my answer for the area goes out 4 decimal places. Have I somehow magically increased my ability to get a more accurate answer out to more decimal places just by virtue of multiplying these 2 answers together? Of course not. Hence, my final answer should only reflect as much or as little accuracy as whichever of these 2 values possessed the smallest amount of accuracy. In other words, my final answer cannot have any larger number of significant figures than either of the 2 values from whence it came. You'll notice that this number here has 3 significant figures, and this number here has 3 significant figures. Therefore, I have to round my final answer so that it only has 3 significant figures, in this case 28.5 square meters. Now, why would I not report my final area with this many digits? The reason is because if I reported this value, I would be telling everybody that I had a device that was accurate enough to measure the width and the length of that room up to 4 decimal places, which I clearly did not. Now I have to warn you, there are actually 2 different sets of rules for doing calculations using significant figures. One of those sets of rules is for adding and subtracting values, and the other is for multiplying and dividing values. I frankly don't know why there are 2 sets of rules, but I hope that you won't get angry at me. I'm just the messenger here. When adding or subtracting values, your answer should have the same number of decimal places as the value that has the fewest decimal places. When the answer contains more than the correct number of significant figures, it must be rounded off. In this example, we're given 3 different numbers that are being added together, with the individual numbers of decimal places in each value being indicated. You'll notice that this bottommost value only possesses 1 decimal place. Therefore, the final answer should be rounded off to have 1 decimal place. This is the rule for adding and subtracting. Now, when multiplying or dividing values, our answer should have the same number of significant figures as the value with the fewest number of significant figures. This rule is slightly different from that for adding and subtracting. When an answer contains more than the correct number of significant figures, it also has to be rounded off.
In this example, we can see two different lengths in centimeters being multiplied together to determine the area. As I multiply these together, you'll notice that I get this final number that has a lot of digits in it. The number that is highlighted in red, in this case 5.2, only possesses two significant figures, while the number here to the left, 6.221, contains four significant figures. Because the value that I used to measure my initial lengths that has the fewest number of significant figures only has two significant figures, my final answer should be rounded off to only have two significant figures, in this case 32. So here's the clincher. Who cares? I mean, why do we care about reporting a final calculation using the proper number of digits? Is this some kind of overly analytical, anal retentive rule made up by bureaucrats trying to justify their jobs' existences? Well, no. It actually does matter. Suppose, for example, that you're an engineer who's been hired to calculate the amount of concrete needed to build a dam. Do decimals matter in this case? You bet. When a calculation could mean the difference between having a dam that is well constructed and a dam that will burst as soon as weight is placed on it. It does matter. So your final calculation should not reflect greater accuracy than any of the individual measurements used to obtain that calculation. And what if you're a drug developer who's calculating the dosage of a newly developed medicine that has a very narrow window of efficacy? Do decimal places matter in this case? Yes, they do. Once again, your final calculation cannot reflect greater accuracy than any of the individual measurements that you used to obtain that calculation. Got it? Good.
This brings us to a couple of different problems that I recently gave my students on one of our exams. The reason, honestly, the real reason why I'm filming this thing is because I feel like I didn't adequately teach my own students how to do significant figure calculations. I feel in that then that I kind of failed them. So I'm hoping to be able to redeem myself by doing so. In one of these problems, we are given the number 0, or 0 degrees Celsius. We're asked to convert that to degrees Fahrenheit. The equation that I provided my students with is that degrees Fahrenheit is equal to 9/5 multiplied by the number of degrees Celsius plus 32. In doing this calculation, I can of course multiply these two together. I get 0 degrees Celsius. Note that because this is a multiplication process, the answer that I put here has to have the same number of significant figures as the value that possessed the smallest number of significant figures. 9/5 here is a fraction. It is considered to have infinite significant figures, whereas 0 here only has one significant figure. Therefore, I'm only going to report one significant figure in my final answer. I now add my 32 degrees, and that takes me to my degrees Fahrenheit. This now requires us to use the proper number of decimals in order to have the correct answer here, because it's an addition calculation. 0 plus 32 is going to be 32. 0 here has no decimals, and this value also has no decimals, so my final answer should have no decimals, and that is the correct answer. The second problem, we've been asked to convert 20 degrees Fahrenheit to kelvins. There might be a couple different ways of doing that, but the simplest way I can see is by converting the Fahrenheit first to degrees Celsius and then converting degrees Celsius to kelvins. Also, I provided my students with a conversion equation that says that degrees Celsius is equal to 5/9 multiplied by degrees Fahrenheit minus 32, and with all of the parentheses in these respective locations. And yes, parentheses locations do matter. We'll go ahead and replace these degrees Fahrenheit with our value we've been given. Presumably, once again, this value has been measured using a thermometer that did not have the ability to measure out any decimal places. As I take -20 and subtract from it 32, I get an answer that is -52, of course. Keeping in mind, this is now an addition-subtraction problem, so my answer here must possess the same number of decimals as the value that possessed the smallest number of decimals. Neither of these have any decimals, so that would be the correct answer to this transformation here. I now multiply that by 5/9. This is a multiplication. However, these 5/9 are an exact fraction, so it's considered to have infinity significant figures. When I do that, I get a number of degrees Celsius, which happens to come to well, it comes to -28.88888888888 off for eternity, I think. It goes for a long ways. However, I have to make sure that I round to the correct number of significant figures. I've got a value here that only has 2 significant figures. Therefore, because this is a multiplication process, the value that I put here must also have only 2 significant figures. So I round it to negative 29. At this point, I now convert the negative 29 to kelvins by adding 273.15. When I do that, I end up getting a final answer of 244.15. Because this is a multiplication, or sorry, because this is an addition-subtraction question, my answer must not have any more decimals than the value that had the fewest number of decimals. This value right here has no decimals, which means that my final answer should not have any decimals, and that would be the correct answer, 244 kelvins. Now we get to the soul-crushing problems of dismay. That seemed really positive. In this first problem, we're given this mathematical calculation. We're asked to determine the answer with the proper number of significant figures. Following the orders of operation procedures that we learn in high school algebra, I guess, we first of all take this value and subtract from it this value. Now the final answer that I end up getting here is like 2.8 something times 10 to the 6th. However, we have to remember that this is an addition problem or subtraction problem, which means that the answer that we need to get from doing this should have no more decimals than whichever value had the smallest number of decimals. In this case, this value here only goes out 1 decimal while this goes out 3. So my final answer should only have 1. At this juncture, I now take this value and I multiply it by my 3.9154. This is now a multiplication process, so when I multiply that through, I end up getting an answer that's like 1.106 times 10 to the 7th. However, I have to make sure that my final answer only has the same number of significant figures as the value that had the smallest number of significant figures, because this is a multiplication process. This value that had the smallest number of significant figures is this value right here. It possesses 2. So I need to be sure to round this so that it only has 2 significant figures, which is going to give me this number right here. In the second problem, I'm given, following the order of operations from basic algebra, I take this number and divide it by 3.2. This is a division problem, which means that the answer that I have to put here should have no more significant figures than whichever value of these two have the smallest number of significant figures. This value right here, 3.2, only has 2 significant figures, therefore my answer here from this process should only have 2 significant figures. That answer ends up coming out to be 1.6 times 10 to the 3rd. At this point, I then subtract from 240.2 this new answer. When I take 240.2 and subtract from it this value, I'm going to get an answer. However, I have to remember that this is a subtraction process, so the final answer should have no more decimals than whichever value had the fewest number of decimals. Both of these values go out 1 decimal place. So when I do this subtraction, I end up getting an answer of negative 1.4 times 10 to the 3rd after I round to the proper decimal place. Now in the last problem, I'm given this number, 0.0045, multiplied by 20,000.0. Now, as I've stated in another video, no zeros to the right count as being significant unless they're to the right of a decimal, which means that this actually, all of these zeros do count as significant. We've got this process, and then I add that to 2013 times 12. If I multiply these two values together, I end up getting 90. How many significant figures do I take that out to? Well, this value only has 2 significant figures. This one has 6. Because this is a multiplication process, I need to take it out to whatever value has, to the same number of significant figures as whichever value had the smallest number of significant figures, which is 90. So that has 2 significant figures. No, it doesn't. That does not have 2 significant figures. Yeah, as I look at 90, that only has 1 significant figure because, once again, zeros to the right don't. Might be confusing then what to do. I could put a 0 after it, but then that would have 3 significant figures. So what do? Well, I change it to be 9.0 times 10 to the 1st. That has 2 significant figures. It's slightly obnoxious, but true. Now I take 2013, multiply it by 12. When I do that, I get an answer of 33,756. Keep in mind, however, that I have to round this to the same number of significant figures as whichever of these values have the fewest number of significant figures, which happens to be 12. So I'm going to round it to the place that would only give me 2 significant figures. So I can change this to 3.3 times 10 to the 4th, I believe. That has 2 significant figures right here in the 3.3. Now I have to add these two numbers, 9.0 times 10 to the 1st, added together with 3.3 times 10 to the 4th. When I add those two guys together, I end up getting a final answer of 3 point some stuff afterwards, times 10 to the 4th. When I think of the stuff, though, I have to remember that this is an addition problem, so I have to round, or I have to make sure that my answer only has the same number of decimals as whichever value possessed the smallest number of decimals. In this case, both of these values only possess 1 decimal, so my final answer here ends up being 3.4 times 10 to the 4th, going out 1 decimal place.